Imagine you came up with a microscopic version of circulation around a curve. In this case, this microscopic circulation is curl. We could picture this microscopic circulation or curl as a bunch of small closed curves where each curve represents the tendency for the vector field to circulate at that location.
Assalamualaikum warahmatullahi wabarakatuh. So today we would like to present our topic, which is analyzing circulation in a wind field using Green theorem. So this is a real-world vector calculus approach. So let's start with the introduction to Green's theorem. Vector calculus deals with multivariable functions and vector, as shown in physics, engineering, and fluid dynamics. It helps describe forces, fluid flow, and electromagnetic fields, all with magnitude and direction. Green's theorem also introduced by Josh Green 1828 and relates a line integral around a closed curve to a double integral over the region it encloses. It simplifies complex vector field calculations and is the 2D counterpart to Stokes' theorem. Last but not least, Green's work later recognized by scientists like Lord Kelvin influenced major theories in electromagnetism. So next, let's go to the statement of the theorem. We divide it into two forms, which is scalar form and vector form. The scalar form of Green's theorem is used when we are working with two scalar functions, p and q, that depend on the variable x and y. Let C be a positively oriented, simple closed curve, and let D be the region enclosed by C. If p and q are continuously differentiable functions, then the theorem is written as below. So, the line integral around curve C of p ds plus q dy equals the double integral over region D of open bracket partial q with respect to x minus partial p with respect to y close bracket dA. So this equation tells us that instead of computing a line integral around a closed curve, we can compute a double integral over the region it encloses, which is often simpler. So next, let's go to the vector form. Here we define a vector field f as p, q, or f equals the vector pq. The theorem connects the circulation of this field around the curve C to the flux of its curl through region D. So, as you shown below, the line integral around curve C of f dot dr equals the double integral over region D of curl f dot k dA. So in this case, the left-hand side gives us the total circulation along the curve, and the right-hand side gives the total rotation of curl within the region. This is especially useful in fluid flow and electromagnetism. So, to summarize, Green's theorem provides a powerful tool to convert a challenging line integral into a potentially easier double integral, helping us analyze vector fields efficiently in two-dimensional spaces.
Alright, let's move to the 1.3, which is the condition for applicability. The first one, we have a region R must be simply connected. This means the region has no holes and is entirely contained within the boundary curve. The second one, curve C must be a simple closed curve. It must form a continuous loop without intersecting itself. The third one, curve C must be a piecewise smooth. That is, it is made up of a finite number of smooth curve segments. The last one, curve C must be a traverse in the counterclockwise direction. This to ensure the curve has a positive standard orientation. The function pxy and qxy, along with their first partial derivative, must be continuous on an open region that contains R. Alright, next, let's go through the application of Green's theorem. There are two major applications, which is in physics and geometry study. For the physics, in fluid dynamics, Green's theorem is used to compute the circulation of a fluid. It connects the curl of the velocity field within the region to the total circulation along the boundary curve. In the geometry study, Green's theorem provides a method for evaluating line integrals around a plane region's boundary, which can be used to determine the area enclosed by the curve.
For the situation 1, in real-world urban planning, especially in densely built environment, understanding non-uniform wind behavior around central circuit areas, such as plazas, cantoners, or open yard is essential. Consider that non-uniform wind field over a circular urban zone equals with the horizontal wind with the square of the x position and linearly with y, indicating acceleration flow as we move away from the center. Moreover, the vertical wind varies depending on both x and y, reflecting the kind of complex directionally flow that may be observed near tall structure or urban domes. So for the first question is, use Green's theorem to evaluate integration closed curve f dr for f is equal to 3x squared plus y plus 2xy, where C is positively oriented boundary of the region bounded by the curve x squared plus y squared equals to 1. First step is we must determine the p and q, where p is 3x squared plus y, q is 2xy, and then we must to determine the py and qx, where py is the differentiate in terms of y and qx is differentiated in terms of x. Py is equals to 1 and qx is equal to 2y. After that, we must calculate the qx minus py. So we got 2y minus 1. We must use the polar coordinate rules to solve this problem. So set the y equal to sin theta in the equation 2y minus 1. We got 2 in bracket r sin theta minus 1. For the next step, we must calculate the region mark of the curve
r cos theta,
where x squared
y equal to
plus
r
y
sin
squared
theta.
equals to 1. And then we got the r equals to 1. Substitute all of them into the equation. So we got the integrates limit 0 to 2 pi, integrate limit 0 to 1, 2 in bracket r sin theta, close bracket minus 1, r dr d theta. And then after we integrate all of the equation, we got the answer is negative pi.
So now let me solve question 1 by using Maple. In step 1, we begin by plotting the curve C1, where we start the command with restart and with plots. This is done using the Matplotlot command. The expression inside the replot function defines the parametric equation of a circle x squared plus y squared equals to 1, with the y values restricted from 0 to 1. The output shows the top half of the unit circle oriented counterclockwise, which match the positive orientation required by Green's theorem. So, for the step 2, we define the components of the vector field. Let m equals to 3x squared plus y and n equals to 2xy. Then we compute the scalar function f from Green's theorem with n respect to x and m respect to y. And it gives us f equals to 2y minus 1. So next, we substitute f in the command y equals to r sin theta, f. And the output gives us f equals to 2r sin theta minus 1. Last but not least, for the step 3, we evaluate the integral. We use the command line integral f.r dr d theta. And the output gives us line integral equals to negative pi. So, this example demonstrates how Maple simplifies the application of Green's theorem by plotting curve, calculating partial derivative, and evaluating double integrals in a polar form.
Question 2 is about, in urban planning, understanding wind flow in restricted spaces like a city block is crucial for improving air quality and ventilation. Consider a triangle region with non-uniform and fine flow, where the wind speed increases horizontally and the vertical flow depends on both components, indicating potential swirling effects. In this problem, we are asked to evaluate a line integral using Green's theorem, which relates a line integral over a closed curve to a double integral over the region it encloses. We are given the vector field f that is equal to x squared y plus ln 2 plus 2x squared dx plus xy plus 2e to the power of 2y dy. The boundary of the triangular is defined by the line y equal to x, y equal to 1, x equal to 3, and y equal to 1 over 2x plus 1. And C is oriented counterclockwise. From the equation given, first, we compute its partial derivative with equation qx minus py, and we will get qx minus py equal to y minus x squared. Now, we evaluate the double integral over the region that lies x from 0 to 3 and y from 1 until 1 over 2x plus 1. As you can see on the slide, we set up the integral using Green's theorem by inserting the function qx minus py with the limit of x and y. Then, we evaluate the integral step by step, simplifying and integrate all of the function. In the end, we will get the answer is negative 27 over 4 as our final answer.
Okay, now for the Maple, in the first step, we define the vector field f using Maple map and apply function. We define 3 parameters per segment, R1, the horizontal line, R2, the vertical line, and R3, the diagonal line. Next step, we plot each parametric curve segment using OPR1, OPR2, and OPR3. The arrow indicate the counterclockwise orientation. The third step, find the curl of the vector field. We differentiate Q with respect to X and P with respect to Y using Maple diff function. Finally, we evaluate the double integral of the curl over the bounded region using Maple int function.